And hello everyone, and welcome to today's class. And today we'll discuss the advanced design of infrastructure projects in InfraWorks and Revit. And together with my colleague Ara Ashikian, we'll present you nice workflows, new tools, and the design software in Autodesk platform software. And let's start with an introduction of your speakers today. So hello again. My name is Jakub Bielski, and I'm working for the Sofistic, which is the German software provider for FEA and BIM solutions. And right now I'm responsible for the development of an application on Revit, which is called Sofistic Bridge and Infrastructure Modeler. One of my duties is as well doing the support and consultancy, and I'm really happy to present some of the workflows that I was doing with our clients.
Yes, my name is Ara Ashikian, and I'm the product manager and product lead on the development side at Autodesk for the bridge and civil structure workflows. My background is many years of bridge design and software development, and I look forward to presenting the Autodesk platform workflows for infrastructure today.
Okay, thank you, Ara. And yeah, so small introduction to the session. So we decided with Ara to present this joint session together to showcase some of the projects and some of the workflows of the different infrastructure projects. So we can see that here we have the bridge, we have the tunnel, an underpass, also the protection gallery. So all of this is connected into one, let's say, infrastructure project family that we'll be happy to show you today. And let's start with the Sofistic Bridge and Infrastructure Modeler. So a few words about Sofistic, who we are, what we do. So we are based mostly in Germany. So there are the two development teams or offices. And but we work together in the multi, let's say around the world, in the multicultural environment. And we have also the partners all around the world. And we are sharing more than 30 years of experience with our clients and also our partners. And here we are historically connected to an Autodesk with the development and starting from the early stages of the software design. And since 2019, we are part of the Man and Machine group. And then let's jump to the Sofistic Bridge and Infrastructure Modeler, so one of the main topics of today's class. So as mentioned before, this is an application on Revit, which helps you to design the infrastructure projects, so simply the axis-based projects in Revit. And due to the very generic software design, we are not limited only by the bridges, but also you can create the tunnels, which you see in a few minutes, but also cantilever walls, and actually what you are up to. We are putting a lot of stress for the shop drawing tools, which help you to create the proper sections and proper sheets. So I will start with the general workflow, how it looks like. So as mentioned before, it's an axis-based design. So which means that an axis is the backbone of the project. We can create one, or we can import it from the multiple sources. Then using this alignment information, we are extruding the superstructure components along an axis using the profile information, the 2D profiles. Then we can also place the substructures or some other components at the given stations. And at the end of the day, we are using this geometrical information and also the information that are input of the axis to create the model-based sketches and drawings. More of this you can find in another AU class from 2018. which is called The Challenges of the Bridge Design in Autodesk Revit, which showcase you more the general workflow of the bridge modeler. So today I will dive a little bit deeper into the specific task or specific topics of the Sophistic Bridge and Infrastructure Modeler. And the first one is the structure parameterization. Of course, that's everyone knows that the infrastructure projects are axis-based, but also they have various geometries. And one of the features that you can actually assign to the structures is that geometry that develops along an axis, which means that even if we have the profiles, we want to extrude it, then we have to focus on an easy input of the different geometrical dependencies and formulas, so we can create the structures according to our wishes and according to the geometrical requirements. So the first part of what you can see on the left-hand side, the parameters plus variables. This is the first way how to parameterize the profile. So simply we are using the variables, which you can see presented as the graph created by the table or by the formula, which represent the values along an axis. And later on, we can take these values and fill the profile with the specific number and create the parameterized variable superstructure. The other way is to use the geometrical parameterization, which is simply the usage of the shape handle points and also an axis. So in this way, we can utilize the geometrical information of an axis to drive the parameterization of the profile or of the components. And how we can do it, we'll take a look at the first project example. And I was happy to create this project together with SNCF. This is the French railway. And unfortunately, I cannot give you at the moment any more project data because it's still ongoing and the data is confidential. But SNCF was nice to provide me with the screenshots and also to enable me to show you the videos. So let's take a look how it works. So at the beginning, we can see the end product, let's say, and this project was really specific because we are working with an archive data. So we had some drawings at the beginning to start with, where we can see the cross section of the tunnel, and actually not much more. But later on, the data, the point cloud scan was done, and we have and so we could derive the cross sections, and later on create the sketches as well, where we can see the points defined on each cross section, and each cross section had also the station information. So in this way, we had the multiple profiles with an outer or inner shell, actually the position of the points in the inner shell. So later on, we transferred this data or extracted simply the coordinates from the points and arranged it together in the manner that we can use later on with the bridge modeler. And we use this data to create the secondary axis, as you can see right now in Revit. So the secondary axis is so-called dependent axis that is created according to the geometry of the main axis and also an offset value in two directions. Next step is to create the tunnel profile based on the old drawings, let's say, that is driven by the shape handle points. And each shape handle points will be later on assigned to each secondary axis. So in the next step, we can see that the assignment was already done. And this small video shows us the change of the rheological deformations of the tunnel along an axis. And this is the end model, or one of the steps actually, where we can see how this model is driven by this axis, and how the geometry is parameterized. Now we can jump into the second part, which is the cross-member array. This is the new functionality in the Sophistic Bridge and Infrastructure Modeler. And in this manner, we can create an array of the already created 3D components, and this this is also depends on how many adaptive points you have. You can, starting from the left-hand side, you can define the position of the segment. This is the part of the tunnel. You can define the position in the middle and also the length of each component. So, for example, this example of the hollow cast bridge, or the segmental bridge. And on the left-hand side, we see an example of the cross-member array with 3 adaptive points, where we have the position, we have the length, and also we can accumulate, and we can also define the curvature of this rail according to the axis. And right now we will take a look at the next example that we got from an Amberg Engineering, and they are based in Innsbruck in Austria, and their client is the OBV, the Austrian Railway. And this is the tunnel. This is currently being modeled in the Alps. So, and it's being modeled with the TBM method. So let's take a look at some of the features. So at the beginning, let's open the connection tunnel between 2 main tunnels, and we can see that actually this tunnel was creating also with the profiles, and these profiles were parameterized in such a manner that the geometry is changing along the connection axis, along the connecting axis. Then we select one of the segments. We can also open the definition of the segments, and we can see that here we have the variable which defines an angle of each segment, and we can see how it's parameterized. So moving along an axis, the relative position of each segment is changing. So later on we can connect all of them, and we can see you can see also with the colors how which segment is connecting, is taken from which family. And also let's have a look at the connection tunnel once again, and you can see that using this method for the proper projects enables you to reach really high LOD, which is level of detail, for the modeling of your structures. Okay, the next part, what I would like to show is the quantification workflow. So the infrastructure models contains also a lot of information that we want to extract later on for example, for the survey takeoff, to share it with the client, maybe to export it to some external software applications. And so a lot of data is already embedded in the geometry of the model. And here we have actually 2 main parts, or 2 main tasks. The first one is tackling with the linear components. So these components are created with the profiles. So here we can select the point. What you can see on the left-hand side, there is the marked point, and this point will later on represent an edge of this bridge. And the second let's say possibility is to select the line which will be extruded and will represent the face of the bridge. So in this way, we go from 0D to 1D, and from 1D to 2D, so 1 dimension higher. Second possibility is to make the survey takeoff for the 3D components, and here is the workflow that will be more straightforward, because the actual geometries are already defined in the families. So here we simply connect the shared parameters with an edge or the face of the 3D family, and of course to the corresponding length of area parameters. And we will take a look at the project. It's an underpass and the rail bridge, and this project was delivered by IBBS from Vienna, also from Austria, and the client was again OBB, Austrian Railway. And yeah, so let's take a look. So let's have an overview at the project. Really nice one, really great project. Together underpass and the steel bridge in one model. And at the beginning, we select the cantilever wall, and we could see that actually the parameters were still 0. The parameters that were later on connected to the given geometries. And right now we are opening the same profile that was used for the generation of this cantilever wall. And we are using the quantification tool and assign in profile command. And in here we can connect the shared parameters that we have imported in this family and in the project with the given point or given line. So of course the length parameter goes to the point, and the area parameter goes to the line. So we have an edge of the cantilever wall, we have the inner and outer walls. Of course, we have to override these families. We can activate the properties once again. And right now, let's select the wall. And we can see that actually the information is not there yet. So we have to tell to Bridge Modeler to refresh the data, to calculate the faces, to calculate the edges, and we can get the values. The proper values. And yeah, let's look around in this project once again. And what I would like to show you, what is really nicely done. Yeah, here you can see multiple axes. What is really nicely done is that actually in one project, in one model, we can see the actual structure, or also an underground, the construction, the sheet piles, and also the earthworks and the anchorages. I would like to show you also the small video that has been rendered by IBBS, and just to show you the possibilities, how much detail you can place in this model while working in Revit. So of course, it's a really advanced project, but yeah, it's definitely doable. And yeah, just let's enjoy really nice renderings and a really high level of detail of this project of IBBS. Okay, right now I would like to jump to other part, which is maybe more connected not with the modeling or the survey takeoff, but with the data management. So how do you manage the models, or how do you actually browse through your models in the more say adjusted manner? So for this purpose, we have developed lately Infra Browser. So this is the new functionality that is available like from this summer. And this is the user-friendly and intuitive tool that enables you to browse through all of the created infrastructure components, so an axis, superstructure, cross members, and so on. And it's also based on the logic that one component is dependent on the next, is connected with the next one, and one is dependent on the next one. So you can see that we have an axis, we have the secondary axis, superstructure, and so on. And we will take a look at it with an example of the protection tunnel, or the protection gallery that is delivered by the WTM engineers from Hamburg, Germany. It's a really nice construction, and it's one of the earliest projects with the Sophistic Bridge and Infrastructure Modeler. And right now we can see that there are multiple components, but we can activate the user interface in our panel, and we can see that the tree is opening, and we can go from access to secondary access to also the cross members, and we can select any given component in this array, or the multiple components in the array, multiple elements we can call it, or simply we can select all of the elements in the array and later on isolate it to see more detailed how it was parameterized, simply when we want to focus on particular components or elements rather than on the whole project at once. Next part is the shop drawing. So as I mentioned before, shop drawings is really really important part of the development, and also it's important collection of different tools that help the drafter or an engineer to create the proper plans and schedules and so on. And here we have also the dedicated webinar on our Sophistic website. So I invite you also to take a look at it. And right now I will showcase you only what you can see in the picture, which is simply the longitudinal section, which is the arrangement of the plan, where you can see that the top view, also the longitudinal sections and the cross sections. And I would like to show you the new developments that are coming soon, and actually at the time of the recording are being in development, but I believe that they will be available soon, which is the creation of the sections and automatic dimensions. So the section views is the command that you know from previous webinars or also AU classes, but right now we have the possibility to select the station manually or graphically in the plan, or simply type in any given station that you want. And when we open the section, we can see that, of course, it's empty. There are no dimensions or annotations, but with the tool dimension elements, you can create multiple dimensions at once, or with the reference dimension, you can at once, or with 2 clicks, you can create the proper dimension based on the cut edge references of the structure. And the last but not least is also the FEA part of the Sophistic. So this is really Sophistic as the software provider is really strong and less about this topic, and we can say that this is our core competence, and we can also offer the possibility to connect your BIM model, so the geometrical model, with the FEA model, which is simply the FEA solutions, and we can derive these 2 models. So we can see the upper one is the BIM model, and the lower one is the shell model. So we can derive these 2 models according to your wish from the geometrical one. So there is also the connection. We can extrude the geometrical data and axes, the cross sections, the variables, and so on. And later on, you can enhance your model with the analytical components. For example, the supports, the constraints, the loads, combinations, and so on. And you can calculate your bridge as well. So with the FEA solutions, I would like to finish my part and hand over to Ara for the InfraWorks workflows, and I'm really looking forward to it.
Welcome, everyone. And this part of the presentation, I'm going to be looking at modeling an interchange with 7 bridges. This is an example case study. It illustrates the fact that in InfraWorks, we can model at very large scale, and we can model very quickly with very high level of detail. In this example, we see on the left the actual interchange, and we see the end model in InfoWorks on the right. If we look more closely at some of these bridges, some of the 7 bridges on this interchange, we can see here, for instance, that we have twin steel bridges on the left with abutments with retaining walls. And you can see the corresponding InfoWorks model that also has all the key elements, the abutments with retaining walls and the piers and girders and so on. All of the components of the bridge are fully parametric. That means that the user can select and modify any parameter. Here's another one of the bridges. This one has an outrigger bent and has retaining walls and has pre-stressed concrete eye girders. You can see the actual bridge on the left, and once again, the bridge as modeled in the overall InfoWorks model. And another look at some of the bridges of this interchange, you can see here on the left, a 2-span concrete bridge, and in the background, you can see a single-span steel bridge. And once again, these are represented in the InfoWorks model, including all the retaining walls and the single-span steel bridge in the background. How do we get there? So let's look at some key steps in the modeling process via this video. In InfoWorks, we can model the roads directly, or we can import all the roads and alignments and corridors directly from Civil 3D. We can also import them via LandXML into Civil 3D from other design packages. In this case, I decided to bring in the road model, but also to bring in all the roadside grading as finished ground, because I want to leverage a tool in InfoWorks that will give me more control on providing the clearance or the opening in the grading for the bridge and retaining walls. So this is called the grading area tool. So the grading area is already being modeled here. So it's parametric or it's vertex based. And once it's there, I chose a transparent texture to it, and then we can modify any of the corners or the whole geometry. It will modify the terrain model for us. In this case, I'm going to specify that I want the slopes to be vertical because we have the retaining wall at the abutments. And we can go ahead and further adjust all the geometry. Not shown in this video is a further approach in Civil 3D called grading optimization. That goes even further, uses computational design to look at all the constraints to do this type of grading for complex retaining walls and so on. The next step is to model the bridge in context. So here you can model in real time the bridge. A default bridge is presented and we adjust it. We're going to change the number of piers to 1, change the number of girders, and switch the default concrete pre-stressed girders to steel plate girders. We're going to say that we want these steel plate girders to be curved and planned. And once we make these changes, it's very easy to make the other spans the same and so on. Working in context means that you can look at the constraints of the site, the point cloud, the terrain model, and so on, and adjust the layout of your bridges. Here I'm now selecting the abutment and replacing it with a custom parametric abutment created in Inventor that allows the user to change any of the parameters to get the desired layout. And now we have kind of the first steel bridge, and I added all the dynamic cross frames and diaphragms and bearings. These are all parametric. And once we have this, we can save this bridge to template, because on this interchange, a number of the other bridges are very similar. They might have different number of spans or different number of girders, but they share the common type of retaining walls and foundation and pier types and so on. So we'll take that advantage of that. So we place a bridge, we'll make sure we have the right number of piers and the right number of girders. But from that point on, we'll just go into the template library and bring the template we just saved, and then add the cross frames and diaphragms. So here you can see how we're modeling all the different bridges. So I jumped ahead. Now you see the others bridges. So we have 7 bridges all modeled in a similar way. And now we might be ready to take this into Revit for construction documentation, adding rebar, adding further elements if not everything was already modeled. So we simply can go from InfoWorks and publish a bridge or all bridges we can publish to BIM 360 or Autodesk Construction Cloud, or if your local computer or LAN network, all of the workflows are available. So once we publish this bridge or this interchange with all the bridges, we can open this up in Revit. All the information, all the high level of detail information is immediately available in Revit. So when we select the pier or the retaining wall, all the parameters are available. We can carry out schedules and so on. We can add the rebar. We can start doing section views and annotations and dimensioning. So in this case, let's have a quick look at some quick section views. Here we can see the twin steel bridges, one of the bridges in elevation, the outrigger bent bridge, the elevation view of that one, or very detailed schedules. This published bridge can also be brought into the Civil 3D road design model, or to create a new Civil 3D model with all the bridge elements and so on. All the parameters also come across into property sets inside of Civil 3D. So we can see here that InfraWorks allows us to work at large scale and quickly model many bridges, leveraging parametric content, and to publish all of this into a central model for use in Revit or in Civil 3D. Now, the next step is, let's look at some of these bridges more closely. Now, the bridge engineers on the team might get involved and say, well, we have this very detailed property-rich model here, so we can extract information for analysis. One type of analysis would be a line girder analysis. This is a continuous beam model where we extract from the physical BIM model all the geometry of the bridge, properties of the girders, and so on, and create a continuous beam model, and then establish via influence surfaces all the live loading and then the envelopes for moment and shear diagrams. All of this is available in these very rich reports. This is leveraging Autodesk Structural Bridge Design on the cloud. And we can go in and look at, in this case, AASHTO LRFD breakdown of strength and stability checks for shear and bending moments. Now, we introduced a refined bridge analysis option that goes much further. So we can go and do a grillage or FE model, and the user dictates all the meshing constraints and high-level parameters, but the information is extracted from the rich BIM model. We can also open this up in a robot, Autodesk Robot, in addition to Structural Bridge Design. So once we select the bridge and the type of analysis model, it creates a very rich, fully calibrated analysis model that takes into account, in this case, curved girders, skewed abutments and piers, and all the intricate meshing to reconcile all the diaphragms, cross frames, girders, and so on. And it provides a very detailed report so that it's very transparent. We can look at this report and understand how every material property is computed, how every section property was derived, and so on and so forth. So the intent is to have a very transparent model that the engineer dictates. How do you go from the physical model into which type of analysis model? And then when you're ready, you can open up this analysis model in either Robot or Structural Bridge Design. So Robot allows for even larger analysis models, or you might start with this model and add, we're focusing on the superstructure now, but you might add the substructure and carry out seismic or wind analyses and other types of analyses directly in the Robot. You can also open up, of course, in Structural Bridge Design and leverage its strength of looking at the design check on highway type girder bridges. So in this case, we can see the FE model and all the analysis representation of the cross frames. Bear in mind, in InfraWorks, they are far more detailed. The parametric cross frames have all the eccentricities and gussets and so on. But when you create an FE model, you're taking the essence and the layout and bringing that into the model. You can see here that the beam elements reflect the spacing and dimensions that are in the physical model. And you might spend time refining the material properties, adding custom loading, and then creating, running the analysis model. And then you have access to all the, of course, the deflections, the beam, the FE stress models, but also we take it a bit further. We integrate all the stresses so that you have along these virtual members, moment and shear diagrams, even though this is a complex finite element model, at the end, regardless of method, whether it's grillage or offset girder continuous beam model, line girder, or FE, we can always have access to all the envelopes of moment and shear diagrams. Now, this allows our users to explore a level of detail, not only for the bridge modeling, but for the analysis that was in the past kept for very late design stages. Now you can do this at the very beginning of the project. And even now, for instance, we might want to explore variations. What if we want to see if a variable depth girder is more efficient? We can interact with the model directly. These are slices similar to what Jakob was showing in Revit. You can vary the geometry along the length of girders with these slices in real time. And once you make the adjustments to one girder, you can quickly assign them to the adjacent ones. And we'll do the same thing on the second span. One thing you'll notice is that all this detailed diaphragms and cross frames dynamically adjust as the geometry of the girders change. So everything is interlinked. So you can focus on the layouts and spacings and the type of cross frames. InfraWorks will really help a lot on taking care of all the geometry. So now we have a variation of the initial bridge layout. In this case, we have a tapered variable depth at the pier. And we can then decide to say, well, let's quickly extract a grillage or FEA model for this variation. Again, InfraWorks allows you to not only model at scale large projects in entire ring roads with many interchanges and bridges, but for any bridge, look at many, many options quickly. So in this case, this is a variation of the initial bridge, and we can bring that into structural bridge design and see how the finite element model now reflects the variation of girder depth and still reconciles all the cross frames and diaphragms and so on. So this is the updated analysis model based on the revised steel bridge concept. What we are working on, and not quite ready yet, but you'll be able to soon make any changes to all the plate sizes directly in the structural bridge design, say change the top flange and bottom flange dimensions, and have all of this brought back into the InfraWorks model so everything is in sync. And the next part is to show, even though we can vary the geometry of girders, concrete girders, steel girders with slices, sometimes you need a lot more precision, or you have to handle much more complexity. So let's take this concrete bridge with the pre-stressed eye girders and make it change. Suppose we're modeling an Australian ANZ type of Super T bridge. These Super T pre-stressed girders are far more complex geometrically than can be represented by 2D dimensions that vary along the span. So it's very simple now. You can go into the girder and simply filter to 3D girders and pick complex 3D girder. You can create your own 3D girders. They understand the relationships of bearings and piers. So if you move and skew piers, they all dynamically adjust, but they are far, far richer in terms of parametrics. So in this case, we can see the Super Ts, and the outside girders will kind of control the fact that we don't want cutouts at the ends on both sides. These are external. So some of the parameters on this specific girder allow us to control the cutout at the end. So I'm going to turn off the cutout on the outside, for instance. Again, there are many, many more parameters because you can control every aspect of this 3D girder, the internal diaphragms, the end details, the hog to represent kind of the camber of the girder and so on. And in this case, I'm also going to vary the geometry of the outside flange because this is a curved and planned bridge and the pre-stressed girders are straight, but with Super T girders, you have custom flange geometry kind of, as you can see on the outside here, and the under external girder will vary the geometry so that the flanges are wider at the ends and narrower at the middle. So again, to model this type of Super T bridge or your own variation requiring more complex girders is not that difficult when you leverage the new 3D girder option. Again, it's all integrated and linked to the geometry of the piers and abutments. So here, once we have one span, we can quickly just assign it to the next, and they will dynamically adjust if the spans are in different lengths and so on. Again, the InfraWorks workflow is meant to allow the user to interact directly with the model and quickly make changes. And at this point, we might decide to say, well, let's do a grillage analysis on this bridge. So instead of going to structural bridge design or equivalent and manually creating all your meshes and grillage models, take advantage of the fact that all this information is already there. You dictate as the engineer exactly how you want the grillage to be modeled, and it will extract all this information from the InfraWorks physical BIM model and allow you to create these fully calibrated, ready to use analysis models. You might roll up your sleeves and make adjustments and further changes, but it's a very good starting point. And the beam representation to get the section properties and so on are there. And from there, you get moment and shear diagrams and deflections to start the design process. This bridge is also can be published like we did earlier for the whole interchange. In this case, let's say we want to publish just this bridge and open this up into Revit. All these detailed complex 3D girders are also, of course, represented in the Revit model. So when we bring that in to the Revit model, you'll see how this information is already there. So it's simply richer geometry, parametric geometry that you can create your own using Inventor, really every part of the bridge, your own piers, girders, bearings, with very high level of detail with Inventor assemblies and so on. Now, we can, of course, take the process in Revit much further with documentation. Jakob was showing some of the really interesting automation they're adding in the bridge modeler there in Revit. Let's now look at an example from a client, in this case, Montana Department of Transportation. They are leveraging this workflow to model the Montana bridges, and they've created their own libraries of very specific abutments and bearings and piers to match exactly the type of construction they like to do in their state. And they are leveraging this workflow. And once they get the bridge published into Revit, they are leveraging Revit to add all the rebar details and do all the construction sheets in exactly the way they like to present them and publish them. So this illustrates how you can go from the parametric InfraWorks model with your own content into Revit with full documentation. So this is for your highway type of bridge. We have another example, which is also the subject of a separate Autodesk University class. I invite you to join that class. It's a super interesting, very large, complex project by Hatch, and it's a project in Canada. And you can see here, this is an InfraWorks model, and they have created and leveraged a workflow to its full extent, created very detailed parametric components for all the complex towers and cables and cross frames and diaphragms. And there's many, many aspects. There are many, many corridors, roads from Civil 3D on this project, many ramps and so on. And they've done a fantastic job of taking advantage of this workflow. And you can see some of the details. And on the bottom right, the published bridge inside of Revit also has all this information. So that's an overview of within the Autodesk platform. Jakob showed leveraging the Sophistic add-in that is quite fantastic to allow you to model directly in Revit and do a lot of documentation. And the Autodesk InfraWorks-led workflow allows you to work at scale in near real time and look at many, many options, including integrated refined analysis, and to tackle highway bridges or very complex large-scale bridges, such as the one you saw here. We will now turn our attention to questions and answers, but before we get there, a quick summary of what we've seen today. Again, the objective today was to present infrastructure modeling in the Autodesk platform. We decided to do a joint class between Autodesk and Sophistic because we are all working on the Autodesk platform. And this collaboration with Sophistic is a long-standing collaboration, and it includes not only infrastructure modeling, but many aspects of building, modeling, analysis, and detailing. And for years, they've been creating very interesting rebar detailing capabilities inside of Revit. And I hope you, I hope this presentation showed you the capabilities that are available for you to use today.